and then we'll give the floor to Ben Spielmann to talk about the epidemiological studies, the risk from indoor radon to children, specifically cancers of the brain and leukemia.
Okay, good morning. I have the privilege to present preliminary results from Task 4.3, a joint analysis of national datasets related to childhood cancer and radon. My name is Ben Spiker. I'm an epidemiologist from the University of Bern in Switzerland, and I'm presenting this on behalf of the entire team, which is quite large, as this is a collaborative study across Europe. I'd like to begin with some background information, what inspired us for this study, and I'm going all the way back to the atomic bomb survivors for what we learned from them about radiation exposure in childhood and subsequent risks of cancer. So what you see here is for leukemia, a graph with modeled risks after exposure at different ages. So the bottom line is the adult exposure during adulthood, and then the two top lines are exposure in children. And what you immediately see, what's very striking is that these, so the y-axis is excess relative risk at 1 gray. So it means that if you increase doses by 1 gray, if you're on the top curve there, you're up over 100 times. So the extra risk is 100 times your baseline risk that you would receive. And this is two orders of magnitude higher roughly than what you, the excess risk for adults. So the lesson learned is essentially that these risks are greatly increased, and then there's a short latency of about reaching a maximum about 7 years, and then these excess risks start to decay. So we learned that children are more susceptible, and this is also confirmed by further studies later on medically exposed persons for various tumors, not all, and that these excess risks occur early in life. So childhood cancers themselves are an interesting entity to look at. These are, of course, medium to high doses, but it's very uncertain how this extrapolates down to low doses. So that is the focus of our study. And of course, when we go to low doses, this is what we're interested in because the general population is primarily exposed to very low doses. This is primarily from two sources, from medical exposure and also from natural exposure radon norm. And the part of medical exposure has greatly increased also in children. There's one part that is therapeutic, which is high doses, but that only concerns a small fraction of the general population. So the large share that concerns the medium, the average dose to the population comes from diagnostic radiation, which is in the low dose range. And there, of course, we're concerned about quantifying the risks associated with those doses so that we can balance the risks against the medical benefits of those scans. On the other side, we have a very different exposure setting. This is natural radiation, of course, chronic, it's ubiquitous. It's far more evenly spread over the population. And we can't escape it. But nevertheless, there are components that we can reduce, that we can modify, such as radon, of course, and norm in building materials, for instance. So there's, again, an interest in quantifying those risks, and also the geographic variation of this exposure across regions provides an opportunity to investigate on an epidemiological level the risks of protracted low-dose exposure. So what do we know about low-dose exposure, cancer risks following low-dose exposure in childhood? And the main evidence, I'd just like to highlight two studies, comes from medically exposed persons. This first study is a pooled analysis of 9 cohorts with exposure of below 100 millisieverts, 100 millisieverts, that should be mistake, yeah. Under 21 years of age. And the results are shown for acute myeloid leukemia, AML, and acute lymphoid leukemia. And although the individual estimates, point estimates here are quite uncertain, you quite clearly see an increasing dose response. And if you would assume a linear dose response, you get these relative risks at 100 millisievert of around 2 to 5, 6. So this is in the same order of magnitude as what is suggested if we extrapolate down from the atomic bomb survivor data. Another consistent evidence comes from the recent EPC scan study, EPI-CT study, which many of you are familiar with. Two studies have been published recently. The studies on blood tumors came out. What I'm showing here are results for CNS tumors. So this is a study involving over 1 million patients who underwent CT scans. And these organ doses in these individuals were carefully reconstructed from historical machine settings. And as you see here, there's a clear dose response here spanning a dose range up to about 300 millisievert. And again, estimates that are consistent with what we find for if we extrapolate down to low doses from the atomic bomb survivor data. Now, as I turn to background radiation, it's important to realize we're going down to the very low extreme end of the dose range. And the doses are more uniformly distributed in the population. So we need very large studies to study any effects. And what you see here is an overview of large nationwide studies that have been conducted in various countries. And I don't want to go, so all these studies have collected cases from national registries of high coverage and randomly sampled controls from large representative data sets from the population. And of course, the big challenge here was for all these individuals to estimate exposures at the places where these children live. So this is a huge methodological challenge and also a cause for much heterogeneity between the studies. So the studies have looked at radon exposure and terrestrial gamma, sometimes also including cosmic radiation. And I won't go into any details in the results. You see there's more studies from leukemia than there are for CNS tumors. I just want to highlight the fact that some studies have attempted to calculate organ doses to the red bone marrow, but there were many weak assumptions that had to be made. So if you see that some studies only, or most studies only had one time point of residence, either at birth or diagnosis. So some strong assumptions had to be made, for instance, that people lived at the same place. And also the dosimetry that was used was, from a perspective nowadays, is quite outdated. And also no studies looked at organ doses to the brain. So given this situation and also the heterogeneity of this results, this motivated us for the Radionorm Task Force 4.3, which is a collaborative study among 5 European countries, France, Finland, Denmark, Norway, and Switzerland, in which we assembled 9 nationwide base studies, register-based studies with geocoded residential history, so full histories back to birth. And we wanted to the extent possible, we wanted to harmonize our procedures. So we collaborated with Work Package 3 to obtain these new organ doses for the brain particularly, but also for the red bone marrow. And we applied what you just heard to our cohorts, which was, for us epidemiologists, quite an intensive calculation, for the physicists, of course. And we harmonized analysis across these studies and then meta-analyzed the results. So here you see an overview of the studies included, the numbers of cases and the numbers of controls. Cases were obtained from national population-based cancer registries, and representative age and sex-matched controls were obtained from the general population. And you see that we arrived at about a total of almost 6,000 cases of leukemia and close to 4,000 cases of CNS tumors. And you see here the numbers of controls vary, of course, we tend to sample more controls per case to increase statistical power. So the big challenge, and I'm only showing some slide, but this was actually the main work, and we've been working years on this challenge of estimating exposure, because what we want to avoid in these studies is to actually directly go and contact these study members. We want to rather estimate the exposure without these people even knowing that they're part of the study, because that's the way we can avoid many biases, epidemiological biases, and we can include large numbers. So all the countries had models that they used in the previous studies for radon exposure and gamma exposure, and then based on these, so these are models that use large measurement networks within the countries, and they're sophisticated statistical models that include predictors, geological maps, or information on residential flats, like the floor level of flats, etc. And we agreed to use these models to estimate indoor gamma effective dose rates, including cosmic radiation. So when we say gamma radiation, we just subsume in there the cosmic component, and indoor radon concentration using these models for all dwellings in which children lived in their lifetime. And then the next step was, of course, to convert these gamma rates and radon concentrations to cumulative doses to the red bone marrow and to the brain, using for radon the new dose coefficients you just heard about, and for gamma radiation we extracted from the publication you see there age-specific ratios of equivalent organ dose to the effective dose, because the effective dose is what we had from the models, so that we could then transfer these to organ doses. So, turning straight to the results, here you see the distribution of organ doses to the red bone marrow on the left and to the brain on the right in the different studies. So these are given here in millisievert, and the bar, the thick bar, spans the interquartile range, so from the first quartile to the third quartile, with the bulge in the middle representing the means, and the line spanning the entire range of the measurement of the doses. So if you look at this, you immediately see we're in the very low dose range of under 30 millisievert, with mean values of around 4 to 9. 3 minutes left, okay, good. So let me carry on. Contributions from gamma, radon to gamma, this itself was an interesting finding for us. So when we looked at the contributions from radon and gamma, respectively, we found that radon contributed only a minor proportion to RDN dose of 7 to 9%, and brain dose, it was much lower, 2 to 3% across the studies. This conceals the fact that for some individuals, these contributions were much higher, because there are some dwellings in which radon concentrations are quite high, so up to, the contributions were up to 30 or 40%. So let's have a look at the results. So what you see here are preliminary results. One country is still missing. We couldn't get in the data in time. And there were some additional tweaks and further analysis that we're planning, so the picture can change still. So for leukemia in relation to cumulative red bone marrow dose, you see here odds ratios per millisievert increase in dose. And you see a fairly consistent picture, the green dots of the effect estimates by study, and then the summary effect from random effects modeling. We will focus on those because there's more conservative yields, an odds ratio of 1.07, so that's a 7% increase per millisievert. Again, consistent with the kind of, is in the order of magnitude of what we expect, with quite a narrow confidence interval. For CNS, the results are more heterogeneous and a bit more unstable, but nevertheless we arrive at almost the same estimator overall, with a much wider confidence interval. 1 minute left, good. When we look at radon dose specifically, we see that as radon is a much smaller component, we see that these results are much more unstable with very wide confidence interval, but nevertheless when we summarize these results for leukemia, we again see a similar effect estimate with a much wider confidence interval, and for CNS tumors there's quite a lot of heterogeneity, and there the evidence is much less clear. For gamma, this is essentially the same picture with some more uncertainty as total dose because it's the dominating component, so I won't touch on that. Quickly want to touch on some strengths and limitations. So limitations include that we have large, poor predictive performance of our epidemiological exposures. There's a lack of information on building materials, which we know could greatly improve our exposures. And I need to finish now, so I'll go to the conclusions. Preliminary results provide support that background radiation increased risk in leukemia and CNS tumors with stronger evidence for leukemia. And I'll leave it with that.